All right, we're back. We are on page 6 of notes 1 of Calc AB. We're doing some derivative stuff. You've just learned the derivatives of all of the trig functions, and you're going to memorize those for sure. Hopefully you have them memorized, depending on if you are watching this the next day or the exact same time. So now let's talk about the derivatives of e to the x and natural log of x, because why not? So let's do the same sort of thing. We're going to go to a calculator page, and we'll see We'll see what it has to offer. So I'm going to add a graph, because I like, for whatever reason, I like to graphically do these and just be like, ooh, kind of like surprised. So one thing to watch out for is when you're using your calculator and you're using e to the x, it's not the letter e, right? It's the mathematical constant e. And that means you got to use this button over here, e to the x. Sometimes I will type out exp parentheses x. It does the same thing. The calculator just converts that into e to the x. So I'm going to hit enter. And this isn't, I think this is interesting. Let me add another graph here, e to the x. Well, look at that. It looks like the derivative of e to the x is e to the x. A lot of graphical evidence there. Let's see what the calculator says here. Let's do the derivative with respect to x of e to the x. So make sure you're using the e to the x key, not the letter e. If you take, let me show you something here. If we find the derivative with respect to x of this e, which is not right, so it's not in bold, doesn't look right, of this, what is that? E to the x natural log of e, what? So that's because you're using the wrong key. So it looks like the derivative of e to the x is e to the x. There's a really famous quote, I think it's from Gandhi, that says, be the change you want to see in the world. And sometimes people like to associate that with e to the x because the rate of change of e to the x is e to the x. E to the x is its own rate of change. It is the change that it wants to see in the world. So that's a little, I don't know, is that math humor? I don't even know if it is. It's just like random facts, really, is what that is. Let's take a look also at the derivative of natural log of x while we're here. So derivative natural log of x with respect to x. So natural log of x is control and then the e to the x key if you want it. Press enter. So this is really interesting because this is wrong. And that's something you just need to be aware of. So why is this wrong? Let me graph natural log of x, and maybe you'll have a good idea of why this is wrong. Look at that. Natural log of x, the domain of natural log of x is x greater than 0. The derivative of natural log of x, therefore, can't exist for x less than 0 because the derivative can exist at most on the domain of the original function. So if the domain of the original is x is greater than 0, the domain of the derivative also has to be greater than 0. Now, if we go back to the calculator page and take a look at the derivative with respect to x of the natural log of x, watch what happens. It's 1 over x, but there's this warning, and the warning has never been more appropriate. The domain of the result might be larger than the domain of the input. And this is an example where it is the case. So the derivative of natural log of x, the calculator doesn't know. It doesn't know, it knows, but it doesn't know that you should never be plugging negative values in there because the derivative of natural log of x, as far as it's concerned, is 1 over x. Plus, let me warn you, human, that maybe there are values you could plug into this that don't make sense. That's what it's basically telling you. So you have to know that, and that's like a really interesting thing. So be on the lookout for that. When it claims the domain might be larger, it really might be. And the domain of the derivative of natural log of x has to be x is greater than 0. I don't really think I can force that. Maybe I can just do this. See, no warning. But why is there no warning? There's no warning because I already stipulated that x has to be greater than 0. So you have to be on your game when you think of that. You have to know that the domain of the derivative of natural log is x is greater than 0 because the calculator will not tell you. And in fact, the calculator just does its thing and then kind of warns you. And I guess you could take the warning as it telling you, but nope, doesn't do it. Seems like such a common function that they could have hard coded that, but they didn't. So let's write this down. So the derivative with respect to x of e to the x is e to the x. It is its own derivative. That's pretty crazy. So like, it's basically the only function for which this is true. There are like other examples. They're just like e to the x though. All of them are basically e to the x. You can like move it left or right and you get the same thing. But this is really cool. This is, it is a function that is its own derivative. So obviously you're never going to forget this one. And then this was way more complicated. So the derivative of the natural log of x is equal to 1 over x, but x is greater than 0. So you need to throw that in because it doesn't know that. Like 1 over x doesn't really walk around knowing that it's the derivative of natural log. 1 over x is like, yeah, give me negative values, give me positive values, just don't give me 0. Natural log of x, on the other hand, yeah, x can only be positive. So I'm going to put a little note here that says domain of derivative cannot be bigger than the domain of function, So you have to think about the domain of the function when you talk about the domain of the derivative. Derivatives can't exist where functions don't exist. And you need to know that. So here is a little table of the derivatives that we now have memorized. That's good. So let's fill it in. So sine, the derivative is cosine. Cosine, therefore, is negative sine. So it's a negative and then the cofunction. Secant is secant tan. So sectan is not a function. Like a lot of people want to make like sectan of x. That's not a thing. You have to write secant of x, tan of x. But I do say secant tan. So I could see where I am contributing to that difficulty, but I do not accept responsibility for that. You have to be your own person. All right, so cosecant, it's negative because it's cofunction, and then cosecant cotan. So those negatives are killer. You gotta remember them. Tangent, the derivative is secant squared. And so cotan, it's negative, and then cosecant squared. And then the derivative of e to the x, be the change you want to see in the world. It is e to the x. And then natural log is the weirdest one. It's 1 over x, but we also need x to be greater than 0. All right. So you are going to memorize these. You must have these memorized. Let me highlight that. This must be memorized. You need to know them. I was doing a good job of staying in the lines, but then, you know, it's too hard. It's too hard. Nobody could do that. Kindergarten was so hard. Okay. So once you have those memorized, you can start using them. If you don't have them memorized, you can't use them, and that's why you need to memorize them. All right, let's see. Find the first 8 derivatives of sine of x. Find the 235th derivative. There's got to be a pattern, or no one would ever ask you to do that. That's a thing. Like when someone asks you for something you see in math that seems really unreasonable, it's probably that there's some kind of pattern or trick or something that like makes it way more doable than you're originally thinking. So I'm gonna make, what should I do? All right, we'll just do, all right, so f of x, I don't know what I'm doing. F of x is sine. I was gonna try to come up with like a really brilliant kind of like notational thing, like a table, but then I decided to do this. So the derivative of sine is cosine. The second derivative of this, so the derivative of cosine is negative sine. And then the derivative, so the third derivative, you can do triple primes. So f prime, f double prime, f triple prime. First derivative, second derivative, third derivative. These are all good. It's going to be the negative of the derivative of sine, so negative cosine. Okay, now the fourth derivative, you don't use primes anymore. You switch to f and you put it in parentheses, the fourth derivative. So you put in parentheses to distinguish it from an exponent. It's not an exponent, it's telling you like take the derivative 4 times. The derivative, the fourth derivative is the negative of the derivative of cosine. The derivative of cosine is negative sine, so it's negative sine, which is just sine of x. This is kind of interesting. The fifth derivative, oh God, that parenthesis went crazy. The fifth derivative is the derivative of sine, which is cosine. The sixth derivative, I see a pattern, sort of, is negative sine. And then the seventh derivative is going to be the derivative of negative sine, which is the negative of the derivative of sine, which is negative cosine. Okay, so check that out. We have this and this, right? It looks like the derivative of sine, and I guess therefore the derivative of cosine, is periodic, which is kind of neat because they are periodic functions. So that's a really neat thing. Is there any reason this pattern would end? Not that I can think of, right? Like it should just keep going forever, which means that I think I can find almost any derivative, right? If I could just find, since it takes 4 to repeat, every time the 24th derivative, 24 is divisible by 4, right? You're going to get 6 and then a remainder of 0. Since you get a remainder of 0, the 24th derivative is going to be the same as the original function. If you divide and get a remainder of 1, right? So the first derivative, the 5th derivative, so the 9th derivative, the 13th derivative, those are all going to be cosine. If you divide and get a remainder of 2, the second derivative, the 6th, so I'm dividing by 4 and looking at the remainder. The 6th derivative, the 10th, the 14th, the 18th, whatever, is always going to give me negative sine. So really what I need to do is I need to find the remainder when I'm trying to do this problem. I need the remainder when I divide by 4. So 235, that 2 is weird. I don't know. Even as I was doing it, I was like, that feels uncomfortable. So now they're out of line. You gotta like not worry about these things. That's my advice. 235. So what do I know? 200 is divisible by 4. 32 is divisible by 4. So this is really 232 plus 3. So the remainder, when I divide by 4, is going to be 3. And if I get a remainder of 3, it should be the third derivative. So I think that F235, the 235th derivative is going to be negative cosine of x. I think that's what's going to happen. Then I think I'm going to check that on the calculator, but first I'm going to do the next problem. And then when I'm done with that, we'll go to the calculator because the next problem says to graph something. Find the equations of all lines tangent to the graph. Cosine between 0 and 2 pi having a slope of radical 3 over 2. All right, I mean, we can do this. So the slope has to be radical 3 over 2, which means I need the derivative of cosine to be equal to radical 3 over 2. So dy dx, the derivative of cosine is negative sine, which I memorized. I need that to equal radical 3 over 2, which means I need sine of x to be negative radical 3 over 2. This is as good a time as any to review your unit circle. So go back through your notes, find a unit circle, review it, see if you can still fill it out. Go for 90 seconds. That's kind of your goal. Get it done in 90 seconds. So sine is negative radical 3 over 2. So that means that x could be 4 pi over 3, or x could be 5 pi over 3. So I know that it's pi over 3, and then it's got to be in quadrants 3 and 4. So 4 pi over 3 or 5 pi over 3. So now what I want is to write the tangent line. So what do I need? I need a point. So, and do I know? Okay, I know I've confused myself here. So let's look at x equals 4 pi over 3, right? So I need to know y is the cosine of 4 pi over 3, and then the cosine of 4 pi over 3 is negative 1/2. So my ordered pair, and then I already know the slope is going to be radical 3 over 2. So I think the tangent line is going to be y minus, what am I doing? Y plus 1/2 equals radical 3. My neighbor just like turned on some really loud thing. I don't know what, like a mower maybe. and it's got me a little distracted. That's where my brain went. And then at x equals 5 pi over 3, y is going to be the cosine of 5 pi over 3, which is going to be positive 1/2, because quadrant 4. So the tangent line, I got like double colons here. That's weird. It's going to be y minus 1/2. Slope is still radical 3 over 2. That was actually given. Minus 5 pi over 3. Ugh. I don't know. Let's go to the calculator on this. I think I got this right, but got that. I don't know. I don't know what device that is, but like I really want to know. That's all I can think about. So we were going to check two things. We're going to check the 235th derivative, which I feel like might be a video ender. So maybe I'll actually do the graph part first, just in case we have to say goodbye there. So the graph of cosine of x, and then I want the tangent lines. So I'm going to go negative 1/2 plus square root of 3 over 2 quantity x minus 4 pi over 3. And then also we wanted 1/2 plus square root of 3 over 2, and then x minus. I feel like this though is like indicative of like how distracting it can be. Ooh, these are like super close. How distracting it can be, and as soon as you get distracted, it's like you just cannot think. So I like when you're in a class, like man, if you're one of those whisperers, you are just ruining it for everyone. And like everyone's always just too polite to say it, so I'll just say it here. You're ruining it for everyone. You personally are ruining it for everyone. All right. It looks to me like we got this. I mean, they definitely have the right slope. I mean, look at that. It's perfect. What could we do? We could have like, let me insert a calculator page. So I'm gonna just type it in. Solve derivative of cosine of x, comma x equals square root of 3 over 2 for x such that 0 x 2 pi. So we get that, and then so yeah, I mean they're definitely right. Cosine of 4 pi over 3, and then cosine of 5 pi over 3. So we got all the parts right. All right. So the one thing that we wanted to check also was the 235th derivative. So we're going to use this, the nth derivative template. And what you can do is you can just fill in a number, 235. 235th derivative of sine of x is negative cosine, which is what we got. So we got it. All right, let's go back. I would say, what's the trickiest thing on this page? I would say the trickiest thing on this page is actually the derivative of natural log. So the derivative of natural log has that domain restriction. In my experience, everyone forgets to write down that domain restriction. So think about it. How could the derivative exist where the function doesn't exist? How could you have a slope at a point that's not on the curve? It doesn't make any sense. So make sure you put that in. Otherwise, I think this is a lot of good stuff for you to think about, and I'll be back in the next video to do some more. So see you then.